Hey everyone, welcome back to The Explainer. If you are gearing up for your CBSE Class 12 Physics Board Exams, you are literally in the perfect place right now. Today, we're walking through the ultimate revision guide for Chapter 1, Electric Charges and Fields. My goal is to help you really lock in these foundational concepts, truly understand the crucial derivations, and most importantly, avoid those common little traps that always seem to cost students marks.
Okay, let's dive into our roadmap for today. We're going to hit 5 major milestones. We'll cover the fundamentals of charge, Coulomb's law and forces, electric fields and lines, demystifying the electric dipole, and finally, Gauss's law and symmetry. Let's get right into it.
Kicking things off with Section 1, the fundamentals of charge. Let's zoom way in to the absolute microscopic foundation of electrostatics. It all starts with this tiny guy right here, the elementary charge, which we just denote with a lowercase e. To put it in perspective, its value is a microscopic 1.6 times 10 to the negative 19th coulombs. And you know what's really fascinating? The whole idea that charge is quantized, meaning it only comes in these discrete, indivisible little packets, was actually first hinted at by Michael Faraday through his electrolysis laws. It was later completely nailed down and proven by Millikan's famous oil drop experiment.
Now, if you're hunting for a classic, easy, 3-mark board exam question, you absolutely need to know these 3 foundational properties of charge. First up, additivity. It just means the total charge of your system is basically the simple algebraic sum of all the individual charges. Next is conservation. Think of it kind of like energy. In an isolated system, net charge is literally never created or destroyed. And finally, quantization, which we just talked about. Charge is always an integer multiple of E, no fractions allowed. Let's move to Section 2 and see how this builds into Coulomb's law and forces. Now we're looking at how these individual charges actually interact with each other.
So when you write down Coulomb's law on your exam, it's vital to know the difference between the scalar form and the vector form. The scalar form, that just gives you the magnitude, the sheer strength of the force. But the vector form includes direction, and let me tell you, direction absolutely matters here. The force that charge 1 exerts on charge 2 is exactly equal but perfectly opposite to the force charge 2 exerts back on charge 1. It perfectly obeys Newton's third law of motion, action and reaction.
Moving right along to Section 3, electric fields and lines. Welcome to the invisible environment surrounding our interacting charges. Now, you might be sitting there wondering, why do we even need this whole field concept if we already have Coulomb's force equation, right? For static charges, it kind of just seems like a redundant bookkeeping trick. But here's the secret. The true value of the electric field really shines when we deal with time-varying sources. See, when charges move, the field around them adjusts. And it does that at the speed of light, not instantly. The field itself actually carries energy and momentum. This is absolutely crucial to wrap your head around because it's the key to understanding electromagnetic waves later on in your syllabus. To actually visualize these invisible fields, we use electric field lines, and they follow some very strict rules. They always originate on positive charges and terminate on negative charges. They form these nice, continuous space curves without any breaks whatsoever. And here is perhaps the biggest one for your exams. 2 field lines can literally never intersect. Why? Well, think about it. If they crossed, it would mean the electric field points in 2 completely different directions at that exact single spot, which is just physically impossible. So the crucial point here is avoiding a super common trap students fall into. Remember, field lines are merely a visual aid. They aren't physical strings or actual objects floating around in space. They have absolutely no mass and they definitely don't have momentum. They're just a really creative way for us to map out how strong the field is and where it's pointing. Definitely keep this high-yield pro tip in your back pocket for those tricky conceptual questions. All right, on to Section 4, demystifying the electric dipole. Let's guide our focus from general fields to a very specific, highly testable setup of equal and opposite charges. So what's a dipole? It's really just a pair of equal and opposite charges separated by a tiny little distance. The defining characteristic, the star of the show here, is the electric dipole moment, which we represent with the vector p. To find its magnitude, you just take the charge q and multiply it by the separation distance 2a. But you have to pay close attention to the direction here. By convention, the dipole moment vector points from the negative charge over to the positive charge.
You are almost guaranteed to be tested on the electric field produced by a dipole. Take a look at this side-by-side comparison for a short dipole. That's when our observation distance r is way bigger than the separation a. Notice anything popping out? First off, the field actually drops off as 1 over r cubed, not r squared like a single point charge. And second, if you look at the exact same distance r, the magnitude of the equatorial field is exactly half the magnitude of the axial field. Burning this visual comparison into your brain is going to save you so much time on multiple choice questions.
So what does this all mean? Let's just pause and think about it for a second. We know what a dipole's own field looks like, right? But what actually happens if we take that entire dipole and drop it right into a non-uniform external electric field? Well, if the external field is totally uniform, the dipole just feels a torque. It's basically a twisting force that desperately tries to align the dipole with the field. But when that field is non-uniform, the whole story changes. Because the field strength is actually different at the positive and negative ends of the dipole, the forces on each side don't perfectly cancel each other out. So a non-uniform field gives you a combo deal: a torque trying to align the dipole and a net translational force that physically pulls it toward the stronger or weaker part of the field.
Okay, bringing it home with Section 5, Gauss's Law and Symmetry. We're moving to the macroscopic level to introduce a seriously powerful mathematical tool for continuous charge distributions. Here's the formal definition, and honestly, we need to give it all the respect it deserves. It's literally one of Maxwell's 4 fundamental equations of electromagnetism. The total electric flux through any closed surface is equal to 1 over epsilon naught times the net charge enclosed. It's just so incredibly elegant. Instead of torturing yourself doing complex, messy Coulomb force integrations, you literally just look at the amount of charge trapped inside an imaginary closed surface. That's it.
And this brilliantly illustrates exactly why Gauss's law is such a game changer. This summary table maps out the core configurations you absolutely have to memorize. For an infinite thin wire, the field falls off as 1 over r. For an infinite plane sheet, the field is actually completely independent of r. It literally doesn't weaken with distance at all. No way, right? And for a spherical shell, if you're outside the shell, it just behaves exactly like a single point charge at the center, falling off as 1 over r squared.
Now, the real secret to crushing these derivations quickly on your exam is something we like to call the symmetry trick. It's how you turn a terrifying calculus problem into a super simple visual puzzle. If your charge distribution is spherical, just draw a Gaussian sphere. If it's a long cylindrical wire, wrap it in a Gaussian cylinder. Planar sheet, slap a Gaussian pillbox on it. If you just match your imaginary surface to the physical symmetry of the object, I promise you the math basically solves itself. Now, what's really interesting about this slide is a pretty incredible pro tip pulled straight out of the NCERT exemplar problems. A lot of times, you'll come across these advanced questions asking about the simple harmonic motion, or SHM, of a test charge oscillating along the axis of a charged ring. Here's the big trap. SHM only works if the test charge and the ring have opposite signs. If they have the same sign, the repulsive force just pushes the charge away forever, making it totally unstable. It'll never restore back to the center. So always double-check your signs. Wow, we have covered some incredible ground in this explainer today. We've totally mastered charges at rest, the precise forces they exert on each other, the invisible electric fields they generate, and how to calculate those fields effortlessly using Gauss's law. But what happens to all these forces and fields when those static charges finally wake up and start moving through a wire? Well, that is a fantastic question, and it's exactly what we're going to uncover in our next explainer on current electricity. Until then, keep reviewing these concepts and happy studying.